Hello everybody, we're back today with more hacking practice. In particular, I am going to be working on a new category since we went through all of the bad random seed challenges from the Nightmare course. We went through all of those on Monday, it being Wednesday for me right now. And probably for most of y'all actually. So we're going to work on the next category, which is the Z3 and Symbolic Execution category. Symbolic Execution, they call out angr. There are other programs that can do that, but angr is probably the most well-known and certainly has a lot of features in that category, let's say. From what I understand, this is what I'm about to say, is that I actually am, of all the things in here, this might be the thing that I am least familiar with to get started on. At least with, even though I've never done like a heap exploitation, I feel like I have an understanding of what is involved with some of those vulnerabilities, so I feel like I could probably just start trying to tackle them. Same with, integer overflows. I don't know about bad file or whatever, the file structure thing, but several of these, categories I feel like I have some exposure to, even though I've maybe not done them very much before. On the other hand, symbolic execution is something that I've sort of had a very small amount of exposure to, much more in not in the really, symbolic execution might not be the right term for what I've done. I've used Z3 as a SMT solver and sort of translated some assembly code into Z3, I don't know, the syntax for their logical relationship representations, definitions, and then had it do the whatever its search algorithm is to find the right inputs. So it's more of a solver kind of thing than maybe symbolic execution itself. Yeah, so basically the little bit that I have tried to learn about symbolic execution has made me realize it's very there's a lot there basically. So I think I'm probably, all of this is to say, I'm not going to go straight into trying to solve this first challenge in the category. It might be an easy one to solve, but it might not be. And I think what I'm going to do is to try to make myself as prepared for that as possible by essentially trying to learn some stuff about angr itself. And then there's I should hit star on that. There's a repo that was actually linked from the angr docs that I was reading just before starting the stream. And apparently somebody has made a similar kind of, I guess it's not similar in the sense that these are not random CTF challenges that would be solvable with symbolic execution. I believe they are explicitly created as a sort of learning resource if you want to learn how to use angr. And since that's what I want to do, and I think I will do better learning it if I have challenges, exercises to work with, that's sort of my plan, is to maybe ping pong back and forth between going through the documentation that they have on the angr website and trying out these individual challenges, looking at this PowerPoint slide that was included with the CTF repo, see if I can find anything useful out of what they describe in the PowerPoint. And basically this is going to be a learning stream as I try to learn how to use angr. And if things go well, maybe sometime within this stream I will get into trying to solve this first high school CTF 2019 A-Byte challenge. I don't really anticipate getting that far in this stream, but I guess it's possible. So yeah, this might be a little less exciting than the previous binary exploitation streams that I've done, because there's going to be more of an emphasis on me sort of reading documentation and trying stuff out than just hammering away at particular challenges. But hopefully going through some of these CTF challenges will keep up the level of activity. So ideally that will be more entertaining than purely me reading the documentation. So we'll just get into it. All right, so might as well follow along with what they have here. We're gonna run Python interpreter, the REPL, basically import the angr library, and then use it to load a project where we provide a binary. So the term project refers to probably the binary itself as well as any analysis. Maybe it's just like the sort of focal point that everything connected to analyzing a particular binary can be reached from. So we'll generate a project based on the true binary. And true is probably incredibly simple. Actually, we could probably check it out in GDB real quick. Okay, we don't have any symbols, so we could check it out in radar though. Yeah. Okay, it's a little more complicated than I anticipated, but not, you know, not especially more. So I think what we're looking at here is like if you don't pass any arguments, I guess if EDI is equal to 1 for passing no arguments, or 3 or more, I suppose if you pass more than 2 arguments, then we will simply return 0. That's what I was kind of expecting. This is a function that just returns 0, but it does have the ability for you to pass in -- help or -- version or something like so. There's a couple, it's a very simple way of parsing arguments that they're doing here, which is reasonable. But yeah, if you do like /bin says true and you pass in 3 arguments, came back with 0, and I'm gonna do test. Interesting. I guess it doesn't care if you pass in -- version or something other than one of the known options. In any case, like that function is very straightforward, and the simplest possibility is you just return 0. So I assume that's why they're starting with it. So we'll go ahead and pop into Python. Angr is currently only supported with Python 3, which I think makes perfect sense given that we are after the date at which Python 2 is supposed to be completely over. So just keep that in mind if you're going to be running it yourself. You're going to need Python 3 for it. angr.project. Okay, so it gives us a warning. It's a position independent executable. So they're just gonna give us a arbitrary base address. I guess not arbitrary. It might be actually specified in the elf headers, but you know, it might not be based there when you actually run the program. So that might be an important element in whatever comes in your analysis. If you're symbolically analyzing it and it's assuming addresses for the instructions are at 400,000 hex, then you know when the ASLR system lays it out differently so that the binary sections are loaded in, or segments rather, are loaded in some other base, then certain elements of your analysis might not be applicable anymore, basically. It really comes down to exactly what your analysis is, whether it depends on those addresses being how they are based in the symbolic executor or not. Okay. Yeah, so we'll be able to dispatch analyses and simulations on the executable you just loaded. Almost every single object you work with in angr will depend on the existence of a project in some form. Okay, that makes sense. So the project is, again, the core thing. And if we do some kind of analysis, we are saying, do the analysis on this project. Interesting. So we can get some properties about the project. That seems fine. Don't know. Interesting. Okay. I'll leave that out because it sounds like that's an optional thing. I believe what they're saying is like if you want the REPL to print the results in hexadecimal by default, you can import this thing, which is neat. Heck it, why not? We'll throw it in there. Okay, so we can say what architecture is it? 64-bit x86 little endian using AMD 64. Find the entry point. It is at 401,7B0, 401,7B0. Slightly different on theirs, but that makes sense. And yep, we can get the name of the file. Yeah, as I say, riveting stuff. Just real important, you know, it's nice to be able to get that info, I guess. So yeah, they have the CLE. I think it's an acronym for like CLE loads everything, like a recursive acronym. And it's, you know, it loads binaries of different formats and presumably with different configuration options. So if you wanted to base it at some particular location or something, by location I mean like virtual memory address. And so let's see. Okay, they'll get to loading later. So you can get the share, like it can do stuff related to the dynamic loading process as well. So it'll find what things it's dynamically linked with and where they would be mapped to, I guess. That's what I'm seeing here. I mean, where it's mapped to, you know, again, much like with it being PIC or something, is gonna, you know, potentially be different if you're running ASLR. But I guess they're giving you what it has been, what has maybe been specified. I don't know how shared object stuff specify where they're dynamically, where the dynamically linked libraries are, well, where the shared objects are loaded in virtual address space. I don't remember if that is in the binary itself. I feel like without ASLR, what they would do is determine a space for it and then use that same address space for any binary that loaded the library so they could reuse the pages, especially if they were read-only, and then maybe do like a copy on write kind of thing. Although copy on write probably would fail if you need to do relocations related to where it was loaded to, so I don't know. There's definitely a lot of details in dynamic loading stuff that I don't grasp yet, but clearly what they're saying is you can, like, it's able, the loader will be able to find that stuff. So let's go ahead and look at what the loader says. So it gives us that address that it decided as the base, and I don't know, you know, why this is the upper extent of the map. Maybe that's just where, that wouldn't be where the stack is, so I don't know. Yeah, you've got a min adder and a max adder. Okay. Main object. Oh, so like this is including the different binaries that have been loaded, I guess. So, okay, these are the addresses that it actually uses for the true binary. Okay. Seems fine. I don't know. I don't know what I would be necessarily like checking it against other than load it up in GDB and see what it says the virtual memory map is. And we can check certain things that we could also see with pwn checksec, but you know, if we are writing Python code around this and we're using just angr, then it's nice to have those available through angr's interface, of course. All right. Okay. So with proj.entry, we can get the virtual memory address for the entry point. And we say proj.factory.block. At that address, we get back a block, which is of type angr.block.block. Okay. And I think it was pp for pretty print, I guess. So this is the beginning of like the stuff from libc. Presumably it's sort of entry prologue. I don't know what the right term is, but what it does before it calls main, part of what it does, because this is probably calling libc start main or something after loading in some position dependent addresses, you know, possibly the address of the main function somewhere in here. Might be this one. So if we minus E4, if we do like what does that look like? Nope, that's nothing. See, there'll be nulls, and I don't, you know, this is some garbage data. Yeah, I don't know what this is a reference to, but that's fine. Okay, so I mean, we don't need to analyze that, but presumably that is the libc entry point. And we can see how many instructions there are. We can get the addresses of those instructions as an array. That's nice. And we could get it as capstone block, or I think vex is their Python internal address. Oh, I see. Yeah. These are the like where Python has heap allocated its Python objects for this vex. What is it called in Python? It's called a field in the dictionary of that object. I don't know, but I think vex is their like IR that they use for a lot of the analysis work. So you could get it directly rather than look at the assembly itself. Okay. So I guess factory is just like an, you know, a sub namespace within the project for convenience functions. The factory to generate a block, for example. But I wonder if I could say like did I say it? Or I do like project equals proj, right? Oh, I probably have to do it the other order. Interesting. So it's just sort of a shorthand for calling block and passing in the project as a keyword argument and the value that you pass to the factory function. In this case, at least, presumably some of these other ones are more complicated constructor functions. Okay, so this is where we get into more of what is about symbolic execution, because the stuff that we saw before is just above this is like binary analysis and, you know, a very trivial amount of like disassembly work. So this is about representing a simulated program state. And we could get the entry state, and presumably that has, we can see we'll get the registers, but it maybe also knows what in theory is in memory at that point. So this one? Yeah. And it is a sim state. It contains a program's memory, registers, file system data, any live data, or what I would consider maybe the dynamic data that can be changed by execution as a home in the state. We'll cover how to interact with states in depth later, but for now, let's use state.regs and state.mem. Okay. So RIP is at the first instruction for that block that we gave it, or for the entry point since we called entry state. And Rax is going to be 1C. I don't know. Maybe that's specified by the System 5 ABI, what the register state is when you pop into like the entry point for a function or for a process when you're executing it. I don't know. But certainly they know because they've figured out what it should be. And let's see. I wonder BV64, like binary value. Oh, bit vector. Oh, there we go. They say it right there. Okay, cool. And we could also get a version of the entry point as an 8-byte, or sorry, 32-bit integer, or bit vector technically. Yeah, Python integers don't have the same semantics because they'll, I think, get promoted into big integers or whatever the correct term is on Python, rather than just overflow, set a flag, stuff like that. Okay, each bit vector has a length. And we can, interesting. What's interesting to me is that we are working with this solver object that is part of the state in order to do this translation to a bit vector and back to a Python integer. Because I'm wondering if like, is there something about the state that, rather than maybe the project which defines the architecture, is there something about it that is why, I mean, maybe it's just like because this behavior is part of the solver and the solver needs to be connected to the state, since you probably need to solve stuff with the process of solving things, so to speak, involves knowing elements of the state, memory, and all of that. I don't know. But I was a little surprised that it's not some kind of utility function just on like the angr module or whatever. So yeah, we can go back and forth with BVV, bit vector value. Okay, cool. And eval to evaluate a bit vector. Since the bit vector knows its length, we just pass it in, whereas when we initialize one, or when we construct one by presumably calling the constructor, well, maybe that might not actually be a constructor function. I mean, it works like one, I guess, right? But we have to pass in the length is the key there. Okay. So we can also just set a value into a register, I guess. What is RSI? Okay. Yeah. A lot of warnings around the fact that RSI has no defined value at the entry point, I guess. But if we set it to 5, then because it's RSI and RSI is 64 bits long, it knows it's a bit vector 64. Okay, cool. So there's a little bit of shorthand where we can just directly throw Python integers into our registers if we need to. And we can do the same thing with memory, but we have to do the equivalent of saying access this address as a long, or I don't know, I think they said integer, so they have int, long. Those are not the terms that I would prefer to use just because of their, presumably they have a fixed size, or maybe the size is still determined by the architecture. I don't know. Maybe there's a way to say like mem something dot and then, you know, int 32 or something of that nature. Oh, here we go. Yeah. So you can say almost, you can use a lot of the C types, including the nice int type one. So unt, etc. Okay. And interesting. So if we say resolved, we get it as a bit vector. If we say concrete, we get it as a Python int. Okay. And you can do other stuff that they'll get to. Oh, yeah. We did that a second ago. And so RDI is also uninitialized. It's a symbolic variable. And that's really how as they say, it's the underpinning of symbolic execution. It's like having these symbolic variables that have either, in the case of uninitialized, I guess unconstrained, it could be any 64-bit value in this case for 64-bit bit vector, or you have a more constrained set of things. Like it could be 5, it could be 8, it could be 7. Maybe those are the only 3 options. But then the logic of the symbolic execution solving process involves checking all of those possibilities combined with all the possibilities of the other things, I think is what they'll get to. But they'll get to that in the solver engine chapter is my assumption. Okay. So there's also a simulation manager. The state lets us represent a program. Oh, I decided in my head, I didn't actually mention on the stream, but I'm not going to try to like narrate the entirety of the text. I've done that before, and it gets kind of tedious on my end and probably isn't that interesting on the end of anybody watching. But I'll continue to point out the things that I think are most interesting, and maybe that'll help solidify them in my head if I mention them. Okay, so the manager allows us to modify the state by simulating execution. Presumably that's the main way it modifies the state, because we can modify the state directly as we did earlier when we set RSI, and we could set random any particular memory address that we want. But this is going to say modify the state as though the CPU were executing it. So that is obviously incredibly helpful. So SIMGR. All right, so we create one of those, and we know which ones are active. Oops. Okay. Can contain several stashes of states. Oh, I see. So the one active and the listing here, I didn't look at it very closely, but these are which states are active. I suppose the reason for that, and they'll presumably get to it later, is as you simulate the behavior of the CPU, you could, when you have these symbolic variables that might have more than one possible value, they're not concrete, they don't have a known fixed value, then any given execution might result in multiple different states as the outcome. And I guess the simulation manager would track all of those states. This is just my guess as to what we're going to be told in a later part of the introduction material. So then we could step, and then we'll step the simulation. So now if we look at state dot rip, it's still the same, so we might have to say state dot active 0 dot rip. Oh, not state dot simgr dot active 0 dot rip dot regs dot rip. Yeah. So we did a step and it didn't go. Oh, it did go. So, okay, just to be clear, well, that's concerning a little bit. What? Oh, yeah, why is it all the way there? We did step, which I thought would step 1. Maybe I should redo this. Okay, well, let's read through what they said, because I basically ended up doing what they did in my confusion, so maybe I'm not too far off. Just to perform a basic block's worth of symbolic execution. We're going to look at the active stash again, noticing that it's been updated, and furthermore that it has not modified our original state. Sim state objects are treated as immutable by execution. You can safely use a single state as a base for multiple rounds. That's nice. Okay. Then why what in the gun? So what I'm thinking is, let's take the address that we're currently at, state.solver.eval. There we go. Okay. So we take the value from the current value of RIP. We evaluate it because it's a bit vector, so we turned it into a Python integer. Then we pass that as the address to the block, and we pretty print to the block factory function, and then we pretty print it, so we can see what the instructions are at the address that we're at. And maybe this is more like what we were expecting. This is still more complicated than I would think the main function is. So if we say, we step again, where are we at now? Okay, so this is something, yeah, we jumped into maybe libc start main or something. And now we have jumped into what might be, or we jumped somewhere into libc, and now we've jumped back into the program. And this still doesn't look like the main function that we were looking at. So did a called that function, and what do we get if we step again? Okay. I don't know. They weren't equal, so we didn't jump, I guess. Like, this is obviously not a great way to be looking at it from the traditional, what is traditional for me at least, see how the execution flows in the dynamic way of just execute something, look at the where we're at in the instructions. So we'll just follow along with what they suggest, because we're not doing that style anyways. It's got several built-in analyses, and yeah, there's definitely a bunch, all with names that don't mean anything to me right now. I mean, maybe disassembly, but Boy Scout, Girl Scout, I don't know what those could be. Okay. And yeah, we could look in the API if we want to know the details of any given one. I don't think I'm at a place right now where looking at that would be helpful to me. Okay. I thought they were going to switch to a different binary, but they're still using bin true. So we get the control flow graph. Okay, so we can say don't load the shared libraries to simplify some of the analysis, I guess. I'm not sure. I mean, if you are going to be stepping through, wouldn't you need to still be stepping into libraries and stuff? I mean, maybe if you're just like, but if you need to know about how memory is being modified by those libraries, I don't know. So we create the project, we create an analysis object, or I guess that's the result of the analysis for CFG fast to get the control flow graph, presumably a simplified one, because there's also CFG itself, CFG emulated. And with that result object, we can ask for the graph, which gives us a digraph from the NetworkX library. I don't know what that's about. The Python library. Okay. So we could diagram it. I guess that's what digraph stands for. And it's got 951 nodes, so we could see the control flow graph as a visual diagram from this if we wanted to. There's probably some function to say like render it to a PNG or whatever. And then we could inspect particular nodes so we could see how many nodes come out of the entry point. Okay, cool. So, I mean, that's sort of a, preview of how you might do more interesting analysis once you have the project loaded. And so we just have, okay. So let's go to the next page. I don't think we're at a point where I'm going to try to tackle the first CTF challenge from the angr CTF repo. But honestly, I don't know if this documentation is new for some version of new, like within the last year or two, or if I simply was not doing a very good job of trying to learn angr the last time, but this right now is like significantly more meaningful to me than any attempt that I've made at learning it before. It's possible that I was in the context of trying to learn it for a CTF and I was just felt so rushed that I wasn't like taking the time to start from the very beginning and go through each step, in which case probably I'm just going to miss things. Or rather get to something and not really have an idea of what it is because I don't have the context for it because I didn't read the earlier stuff. Like, this doesn't seem like something where I could just be like, oh, I know that I need to use something related to execution engines, so I'll just pop into there and start reading or whatever. Okay. So they have an example in the angr project. Let's see. Where would these examples be? Okay, it's not in the angr project itself. So what am I, did I skip over something important in the installation? Oh, here's an examples page. Okay. It's in angr doc. All right. I like this. I'll go through these examples as well, perhaps. Oh yeah. They just have a bunch of CTF challenges and like how can you use them for that stuff. That's great. Okay. Might as well grab this. Don't really want all of the docs. Why not? Grab this. What is it? I forget the names of the commands. Is it a sparse checkout? Yeah, okay. Just refresh myself on the names of stuff, the commands. Knit cone. I think this is not actually the blog post. There we go. This is the blog post. I saw the useful examples in. Partial clones and okay. So if we clone this, oh, I just want to, and then oops, not done apparently. Right, now we do init. Do we, what? Boo. I'm on some old Ubuntu, it doesn't have. All right. We will, in fact, get everything. It's probably not that much because it's the docs. That's what I'm going to tell myself. Yeah, that wasn't so bad. Okay. So no, I want. You know what? Okay. And we want does it work? Cool. Okay, looks fine to me. Different high end of the address space, but I don't know that I should care. The loader represents an entire conglomerate of loaded binary objects. So there are objects that the loader will represent that are not it's the address space for the kernel. I don't know if this is the like VDSO or what. And then there's the thread local storage object. Okay, so presumably it's doing as close to exactly what the kernel and sort of user space dynamic loader would be doing when you load a binary. So that's neat. Okay. Although the externs thing that they mention in here to provide unresolved symbols, it has a particular address that it's like address space that it's mapped at, but I do not know what it is, what it's supposed to be there. So that's a new one to me. Oh, I think, okay, they say it's they use it to provide addresses for unresolved imports and angr internals. So I think that is not a thing that would exist in the memory, in the virtual memory space when loaded for real. And the kernel object is the VDSO thing. Okay. Ooh. And then you can look up basically a reverse lookup in the map. So you can provide an address and it'll give you back the object. That's nice. And you can get the segments and the sections if they're in there. You can look up a segment or section by giving an address and it will find it for you. Reverse lookup kind of thing. Cool. can also get the PLT stub, and you can do the reverse of that as well. That's nice. So you can get the pre-linked base of the object, and the location was actually mapped into memory by CLE. So I'm wondering if there's some way of simulating ASLR with CLE, and therefore it would actually map it at a different base. I don't know. All right. Yeah, this one is not as obvious to me. I get the other two, and I've certainly heard the term RVA in Windows land. But how is an address relative to the object base different from an address relative to the pre-linked? Okay, so in this case they are the same. So it's not relative to the main object or anything. It's relative to the object that it's in, which is the thing that makes the most sense. But I guess sometimes these will be different. Or maybe they are always kind of the same, but you would use this term if you are more focused on Windows stuff. I don't know. You can see what object owns it. Cool. Okay. This is what I was wondering about, because if we say like find symbol string compare, it's like, hey, here's the string compare from libc, which, you know, good, but there's also sort of that concept of the having that symbol in the binary, the non-lib, like the program that loaded or linked to libc, which is how the relocation stuff works, I would say. So yeah, so if we just directly ask the main object and say, get me the symbol called string compare, then it's willing to give us the one from the main object and indicate to us that it is an imported symbol. Okay, and then we can find what it got resolved to by the loader. This is really great. I mean, just from like standpoint of being able to investigate stuff and get a better understanding of the loading process, I can see this being useful just to play around with, even outside of using this when you're doing your symbolic analysis, symbolic execution stuff. Several months ago, I was working through some parts of a book called Linkers and Loaders, I think. Yeah, which I would recommend to anybody who wants to know a lot of the low-level details of how static linking and dynamic linking and loading of executables works. It's not particular to Linux, I don't think, in my recollection, but it definitely, applies to it, as well as probably applies to Windows, because it's just talking about the techniques, and ultimately those same mechanisms, or the results are necessary in any kind of any operating system where you're going to support dynamic linking or something will have necessarily the same concepts about like relocations and stuff. So highly recommend that book. And I think if I go back into it and continue with writing a version of they go through and have software or have examples where they're building an actual linker. And I think if I go through with that, then being able to also play around with that stuff in angr might be helpful, because I'll know that it's been done correctly in here as a simulation of the loader that I can like introspect into, and sort of compare against the results that I am getting from my loader or my linker software or whatever. But I don't think I'm going to be doing that anytime soon. I've got the decoder project to work on in the meantime. Gonna just double check that the audio is actually working. It looks like it's working in OBS, but I've seen that and been tricked by that before. Maybe a little too quiet, but otherwise seems to be working. Okay. So if we get flash.loader.main object.imports, we can see where things are. Like, I don't even know on these addresses. So we've got relocations associated with each symbol, and are these gonna be, no, yeah, I'm really unclear on what these addresses are, and they don't seem like they are sequential enough, like packed together sequentially enough to be in the global offset table. And I guess like the global offset table is when you want to do lazy reloading, or lazy dynamic linking, not reloading, but like gets resolved at runtime rather than at load time. So if we get 1, which will be puts, if we just ask for puts in there, an owner is going to be the main object, and what did they say, symbol. We can get okay. I don't know. Don't really know what these addresses are talking about. Could look at the source code and find out, but I'm not going to bother right now. Okay. So I guess with forced load libs, you could simulate LD preload behavior. Just force additional libraries to be loaded. Okay, so you can override things like the base address and the entry point. here's what I was thinking, or asking myself about earlier on with if you load the binary and say don't load any of the shared objects that it is linked to, how does the simulation work if you are then simulating, if you're symbolically executing the program? And I guess they have basically fake, like, Python implementations of those functions that perform the same state manipulations, but then don't need to. We can see the list of those. Yeah, probably a lot of stuff for like glibc. So then you don't need to symbolically execute those, especially if you simply don't care about the details. If that's not part of your analysis work, it still has to be simulated, but you can simulate it in a much faster way than going through the true symbolic execution machine, I guess. That's cool. And okay, and it just, maybe it's not even about being faster, but it certainly will cut down on noise or additional information that you need to worry about in your analysis results, because we're not tracking the analysis details of that. But I guess there's some potential for them to be slightly different from the real world implementation, which okay, so yeah, there's, it's just possible that the simulations that they have are not perfect. Okay. So they also have a sort of fallback default sim procedure that just returns a new unconstrained symbolic value, which seems, I mean, maybe it's better than just quitting out and saying, hey, we couldn't do it. But if you, like, the return value being unconstrained is fine, but you don't have any concept of whether or not memory was modified or anything of that nature. And I don't know if that is properly represented by returning a unique unconstrained symbolic value. Maybe it is. Okay. Yeah, so that, you can customize which functions get represented, get overridden as sim procedures and which don't. Okay, so you can put in your own hooks. What is length equals 5 on that? Oh, I see. Okay. Cool. That all seems good. Now we get into maybe the meat of it. Trying to decide if it's worth me still streaming this, because I think I'm probably going to try to get through maybe up through the try to get through all this section of the core concepts before I actually start working on the CTF challenges for angr. And I can't imagine this is actually very interesting to watch. So my thinking is I'll just do this on my own offline. We'll come back on Friday, which is the next day where I do binary exploitation practice. And I'll make sure that I'll be in a position to actually start working on those CTF challenges from the angr CTF repository. And that way there's something a little more interesting. I'm in this I don't know, halfway point of the main reason that I'm streaming is to keep myself on a regular schedule of working on this stuff, because it would be very easy for me to put it off and say, oh, I've got some other projects that I should be, in any given night, say, oh, tonight I'll just keep working on this other project that I have going on right now, and I'll do some hacking practice another time. But doing the streaming thing, having that schedule helps me make sure that I actually do it every day. So that's the core reason for me doing this. Secondarily, though, if there's gonna be people actually watching, I don't want it to be a really boring experience. And unfortunately, some of the aspects of it where I'm simply learning something on my, for myself, doing it the first time I've ever done this, I'm going to need to read a bunch of stuff to learn how to do it. I don't know that that's actually a very interesting experience for an audience versus me actually going through and practicing the skill. Even though, I don't know, me going and practicing angr, using angr might not be that interesting if you don't really know anything about angr, but I also get a feeling that lots of people that watch my stream or have watched previous streams where I was working on some of the other binary exploitation challenges aren't necessarily experts in that stuff either. So, it might be the same thing, but at least me doing something active is probably better content for the stream. And yeah, so I'm gonna try to manage my time a little bit better to make sure that when I am actually doing some streaming, there's real meaningful content for y'all. We'll come back tomorrow with continuing to work on the x86 decoder project. I need to also do some offline work for that, where I sort of get things prepared in terms of maybe having a unit test library integrated, and maybe having some of the boilerplate helper code taken out, like already done, related to printing out results and stuff. So effectively, yeah, I need to be more cognizant of the fact that, even though a lot of this is done for my own benefit of the practice and the results of me keeping up with the practice, if I am doing it in a way where people are, showing up and might want to actually watch what's going on, I should probably try to make it at least a little bit compelling. So, gonna end this stream. We'll come back tomorrow, work on the x86 decoder, come back on Friday, work on the CTF challenges for angr, and I don't know how many of these I'll get through before I decide, like, hey, maybe I'm now in a position to work on the ones from the Nightmare course. If it goes really poorly, if I'm just like really having difficulty getting through any of these, then I'll probably set angr aside entirely and switch to the ROP stuff that is following this category, and I'll just have to come back to this category at some point. But I am really interested in gaining the skills around symbolic execution and being able to do this kind of more, I don't know, I in my head I sort of associated with academic kind of stuff, like, whereas some maybe the low level hacker kind of stuff is like just culturally and conceptually in my mind, it is not a very high art form, let's say. It's like you're simply tinkering and noticing details and connections between things, and all of the details that you've learned about something, about some implementation. Versus symbolic execution is like there's a lot of theory behind it. There's obviously a lot of mathematics underpinning like how symbolic execution works, how an SMT solver works, those kinds of things. And then they've built tools on top of all of that implementation of real meaningful theoretical stuff. So it feels like it's coming from a very different cultural basis, and I don't think it's a coincidence that this tool has its home at one or two universities. I think maybe New Mexico, or is it Arizona? And then also Santa Barbara, UCSB or something. Yeah, Arizona State, and Santa Barbara, University of California. I don't think it's a coincidence that the main motive force, let's say, underpinning this is people that are in an academic scenario, versus, I don't know, I see a lot of tools that are just people like me, right? I didn't even go to university, so I don't have that much of a connection to that culture and that whole thing. But like, I've definitely spent time learning weird computer details and have been able to come up with stuff out of that, basically. So I don't know, I'm just completely rambling at this point. But I think, oh yeah, that's what I was saying. Like, the fact that it's it does feel like it's in this separate category of tools and approach and just culture in the realm of hacking and binary analysis stuff, makes it have its own kind of appeal, because I want to feel like I am not limited to, oh, I can do an exploit using a ROP chain and maybe exploit a heap vulnerability, but anything that involves some like mathematical thing like symbolic execution, I mean, there's been no math in what we've seen so far, but like certainly it's based on logic, to put it very, very broadly. I want to feel like these are still things that are accessible to me, even with my lack of any higher education kind of stuff. So just giving some background on why, even if I find this to end up being very difficult, I want to keep pushing on it, because I don't know, just because it's difficult doesn't mean that I can't overcome that difficulty. Okay, this will be the end of the stream. Unfortunately, very short stream this week, because I started to feel like this has got to be incredibly boring to watch me read through documentation for multiple hours. So I'll make the next streams more interesting, and over the weekend we will get into Try Hack Me, and that should be more accessible and more interesting for y'all. So thanks if you tuned in or are watching this on the VOD. Gonna end the stream now.